Hello everyone and welcome back to another video. Today we are continuing our series of learning C, and today we will be talking about memory allocation in our program. Now, my original plan for this video was to talk more about pointers, which are very essential in C and C++, but I don't think we will make it just there yet. I realized that memory is actually a very important topic in C, and we should spend some time on it first. Now, just a very quick disclaimer, I will be making some references to different number systems. What I mean by that is like your binary number systems, because obviously that's the language that your machine reads. And it's very essential for you to learn it. Now, I would actually recommend that you have a solid understanding of this because that's essentially how memory works. It's a bunch of zeros and ones. That's all binary is. Now, I might be making a separate video on that topic if I see that it is necessary, but if that's not up by the time that you're watching this, there are a lot of resources out there, and you don't have to get too deep into it. I would just get a very decent understanding so you could wrap your head around this stuff. Now, what is memory? Memory is, of course, where we store everything in the program, all of our data, you could say. Now, memory is actually broken down into just one big array. Now, if you remember from Python, an array is just like a list. It has a bunch of elements to it. And, whoops, just draw this like this. It's broken up into different boxes. Now, in memory, each one of these boxes is called a byte. Now, if you're familiar with binary, you most likely know what a byte is, but, well, 1 second here. This is a byte. And this is actually a group of 8 bits. Now, a bit is actually just a box which stores the values 0 or 1. Simple enough. Now, with these number systems, we can actually represent different numbers. Like, for example, the number 10 in binary is actually, well, what is it? It's 1010, right? This is in the decimal number system, and this is in binary. And these are equal. And the reason why we prefer to use binary is because our machine, our computer reads information as a bunch of highs or lows. It's either this or that. And that's what binary is. Now, okay. So, how does this all work? Well, let's say, for example, this is a very good analogy for how this array works. Imagine that this array is actually just a street, and a street has a bunch of houses, which are what we will think of as, our bytes. Now, of course, these bytes store data such as variables. They could be whatever you want. They could be an integer, a float, a character, whatever you choose it to be as the programmer. Now, imagine that this tree of houses, right? In one of them, let's say this one, we're throwing a birthday party. Okay, that's cool. Now, let's say you have a friend over here, and you come over to this friend and you want to invite him to your birthday. Now, here's a question. Do you think that it's very efficient for you to bring the house over to him and bring the entire party to him as a way of, inviting him to the birthday? Or instead of that, would you give him some sort of invitation which tells him the address of the house? Now, obviously, the second option is a lot more efficient. You don't have to move a whole house to invite someone to your birthday. You just give them an address. And these addresses are actually how how RAM works. It receives addresses of memory, and now instead of a friend here, we have a CPU, which is basically the brains of your computer. And whenever this CPU requests to load or store data from RAM, well, is it efficient to just hand it over like 5 or 6 or how many ever bytes? Or is it actually more efficient to, you know, give it an address, point it towards that section of data? Now, when we say give it an address that points it, that is obviously a pointer. If you've ever heard of it before, you probably figured it out by now. And we won't go too deep into how pointers work in this video, but we will in the near future. Now, okay, now thinking about that, this memory, your program has its own designated memory. Your computer obviously has like one big memory for the entire operating system, the entire machine as a whole, but your program actually has one big designated memory, and let's just represent it as one big box. Now, the operating system actually tricks your program and makes it think that this one big block of memory is actually all of the memory in your computer. And so your while let's say this is your entire memory, which obviously wouldn't be just this many bits, it would be a lot more. Well, actually what might happen is maybe these are, for example, the memory dedicated to program. Dedicated to program. And this chunk actually ends up being represented by this box for now. And obviously, because we are tricking it into thinking that this is all the memory that we have, well, it thinks that it starts off at 0. And what I mean by 0 is its address is 0. The true 0 would be the very beginning of this array. Now, it's going to think that this starts off as 0, even though obviously this chunk doesn't start off at 0. It's not equal to 0. We don't know what it is, but it's not equal to 0. Okay, and it goes up to some number. Let's say 2 to the 32 minus 1. And this is just a 2 to the exponent of something, which is significant in binary. We won't talk about that too much right now. Just a big number. Let's pretend that this is the last bit. Last address. Okay. Now, from here, we break up this box into different sections of memory. And the first section is actually your text. Now, what do I mean by text? This is your actual code, which ends up being compiled. Okay. And from there, we have another section. And this here is actually called your, well, data. And obviously all of this is actually data, but this is your predefined data. And that just means it is statically defined. And what this means, more simply, is that this is the data that we actually, its lifetime is known. And what I mean by that is we know how long it lasts. Okay, we're not going to get rid of it. We know that beforehand. Well, we know when we will get rid of it, for example. So, lifetime known at compile time. And that's important because we know that we know the size of it at compile time. We know the size of it. We know it's not going to grow and it's not going to shrink. If it's going to grow, then we have a problem. And if it shrinks, then we actually wasted some resources. Now from here, we actually have what's called a heap. And if you know your data structures, this will sound familiar. We won't talk about it too much, but this basically has your dynamically allocated data. And what's important about this is actually the lifetime is not known. Lifetime is unknown. Unknown at compile time. What if this is an array that continues to grow depending on what your program does, right? Well, we can't actually predefine it. We can't give it a set of data already. We have to give it space to grow. So actually, we draw this arrow here because we know that this can grow. Now, we do have one last bit of data, but we can't put it on top because if we put it here, well, this heap will overwrite it. So what we do is actually we start it at the top. And this is our stack. And this is another data structure. And this one I will explain to you because it is very simple and it is pretty important. And this stack is actually statically allocated data. And the lifetime of this is, the lifetime of this is dependent on scopes. Do you remember scopes from the last episode? Dependent on scopes. And we will, okay, let's quickly go over what a stack is actually. Think of some box, some container, right? This is all a stack is. You have a piece of data here and I want to put it into the stack. So I put it in. Now let's say I want another piece of data in there. Well, if I put it into the stack, I put it on top. So if we number these, we get our 1 and our 2. But if I was to pull out of the stack, we actually put what we most recently put in out and then the 1. So this is what's called a LIFO data structure. Last in is first out. And now why is that important? Well, before we talk about that, notice that we said it can grow, right? And much like heaps, we can't just restrict it to a certain amount. So actually we also have an arrow and it grows downwards. And this space in the middle is just an unallocated space, which our heap and stack can grow into. And if they were to meet, well, your program would be running out of memory, so it would probably slow down a lot before they meet. But then you end up with a lot of other issues if they do eventually meet. And the takeaway from all of this is, well, static memory, and that is allocated at compile time. So before the program runs. And dynamic memory. And they work together. And this is allocated during runtime. Okay. Now, what do we mean by scopes, obviously? Well, let's head over to C finally. And in our Visual Studio Code, well, let's write a simple program. Let's include our standard io.h just so we're able to print. Obviously, we need our main. And let's just return 0 right away. And you know what? Before all of this, we're going to make another function that's going to, well, return main, but return something, but it won't really matter. And, oh, we can't use double, and that's because double is a it is a name for a variable type, so we can't use it as a function name, but we can use double with a capital. And you'll see why we're using double. And now here, right, this will be taking an integer x as a argument, or parameter, sorry. And what this will do is actually it will go x is equal to x times 2. And we will return 0 because we don't care about what it returns. We can return x as well, it does not matter. And here we'll actually create an integer x, which is, let's set it by default equal to 10. Okay? And we will print f and say x before, and remember %d, and then we give it the x. And here we're actually going to call double, and we will pass over whatever that value of x is, and we will print x after. Now, before we run this program, what do you think will happen? We pass this value of x into here, we double it. Well, surely when we print it again, it should be doubled. It should be 20, right? Well, let's see why that might not be the case. First of all, remember, always compile, give it a name memory, and then we run memory. And see, well, first of all, we forgot to put our new lines, but x before is 10, x after is 10 as well. Well, what happened? Well, let me just show you this. If I print it here, and I say x intermediate, and pass over this, and then x, and this, and this time, let's create new lines. Okay, and now if we were to recompile, well, it is being doubled, it's turning into 20, then how come it's turning into 10? Well, that's how scopes work, and this is how the stack actually ends up working. Within our main, right, pretend like, well, this is our stack, right? And we have this x that's equal to 10, right? And then after, when we call double, well, what's actually happening here is we're passing the value of 10 here, and we're setting it to this x. But this x actually ends up being pretend like now this is a box of data, and we're going to put it on standby because we're putting a box of data on top. And this defines a new x. X is also equal to 10. They have the same names, but they don't have the same addresses. These two don't share addresses. And it's not the names that make them the same variable, it's the addresses. And the important takeaway from that is after, when we double it here to 20, well, this is not being doubled. And when we return 0, so we exit this double x, we exit this function, and we end up here, what ends up happening is, well, we just exited the scope. We get rid of this box that holds that x. We don't need it anymore. We're past that. And then we go here to print x, and well, it uses this one because that's the same x that it's referencing to. Now, here is a better, let's talk about a better example for this. Let's say our double actually took another integer called y, and this y specifies how many times we want to double it. Okay, so let's also specify a y here, and we want to double it 3 times, just to keep it simple. We're going to be printing x and y before, and let's just print them like this. %t, x and y, and we'll copy paste this. Okay. And let's say we want to store our answer, an integer answer. And it's nothing for now, but we store it equal to whatever this returns. And here, whenever y is equal to 0, we want to, well, that's an O, not a 0, return whatever x is now. Otherwise, we want to double x. Actually, we want to also get an answer here equal to, and we actually need to define an integer answer. And we'll go over what all this means in a second. And we want to multiply x by 2. And we want to decrement y by -1. And let's not print it for now. And we're going to return answer. Now, what will this actually print? Well, let's see. GCC, what did we name it? GCC memory.c overwrite as memory. The function double. Oh, and that's because here we forgot to pass the y. Now, if we were to do the same thing, now call memory. Now we print 10 and 3, 10 and 3. Well, we don't want to print x and y actually. We want to print the new answer, which instead is actually just let's just set x equal to this, okay? X and D, and we'll print x here. Okay. That should be it. 80. So we're saying doubling 10 3 times gives us 80. Now, how does this all work? Well, pretend, of course, that we have our stack, right? But, of course, this stack is actually broken up into different layers. This is how we'll represent our stack. We'll just fill it from the bottom up, and what we need to remove, we'll remove from the bottom down, because it's a LIFO function. Now, how does this function work? This x is equal to double. This is like calling this function, right, and replacing this with whatever we return. Now, on here, right, we actually have defined an integer x as 10. So x is equal to 10, right? Now, we have a y is equal to 3, right? And, actually, if we were to do, this might be a better way of explaining it. Into x, and we'll just directly pass in the 10 here. And just to show you that this does the same thing, well, because we don't have an x here anymore, we don't have an x, this is our previous number that we're passing. We get 10, 3, and 80. Okay, so we actually have defined a y is equal to 3, and we've defined an x, but we don't know what it's equal to yet. And what ends up happening is actually we move on to the next scope, and this is actually here, this is double, but we are passing in 10 and 3. And what ends up happening here is actually, well, we have an integer x, which is equal to 10. We have an integer y, which is equal to 3. And we have an integer answer, but we don't have an answer to, it's not set to anything. It's actually equal to this next double. And we extend this here. This ends up being double of, well, we multiply it, so 20, and we decrement, so 2. So we get an x equals 20, a y equals 2, and a new answer equal to nothing. And let's just extend this beyond. Sorry about that. Let's just do this. And now our next part of the scope is, well, it's another double, but this time we double 40 and 1. So x is equal to 40, y is equal to 1, answer is equal to nothing. And let's just clear up some space. Apologize if this is getting messy. And this right here ends up being double 80 and 0. So we define an x equals 80 and a y equals 0. But notice here, if y is equal to 0, we just return x. And this return basically means we exit this scope. So what happens is this 80 is returned to answer, and we delete all of this. And now here we go back to the last function where this is called. Now remember, we set answer equal to double of this. And we are returning answer, right? So this answer actually returns back here. So this is 80. And we've exited that scope, so this all disappears in the stack. Now we go back. We set answer equal to whatever the answer is, and we've returned answer. And it sounds like it doesn't make sense, but this is what recursion is. We're calling the function from itself. You don't need to know that too much, but the important part is now is you can see how the scopes are actually all closing, and we are just returning all the way back to the original. Right here, and we're back with our initial data set. And all of these function scopes are gone. And we're back with a value of 80. Important thing to take away from this is how our scopes actually closed, how the stacks in them, how the variables disappeared from the stack. And just a side note, just remember when we go variable equal to a certain function, well, it's as if we replace this double with whatever we return. It's like we replace this double 10y with the answer, but obviously we had to compute the answer first. And that's pretty much it for today. Thank you guys for watching, and I'll see you guys in the next episode.